Here we are inside the Hera astrophotography processing interface. This is the pre-release version 2. This is software that I've been writing myself since about August 2021, gradually adding new tools and building the interface that hangs them all together. The processing starts with the stacked image. I'm going to use an image of the Rosette Nebula with a total integration time of 7 hours and 15 minutes, and I've stacked it using Deep Sky Stacker. To open the image, I add an Open Image command to the sequence by selecting it from the toolbar, and then it appears in the sequence editor in the bottom right, and opens its settings panel in the top right. All I need to do is hit the folder icon and select the input file. Selecting Open Image in the sequence editor shows a preview in the preview pane, and since the output of this step has now been computed and saved in the memory, a check mark has been added to the step in the sequence editor. The histogram for the selected step is also shown at the bottom. It currently defaults to 8-bit or 256 bins, but we can put it into 16-bit mode if we want. This obviously doesn't affect the data itself, just the presentation of the histogram. Clearly the image is very dark, as you'd expect for a deep space image like this. The first step is just to have a quick look at what's there with a rough and ready stretch. And for this I will add an instance of the histogram transformation tool, which then appears as the next step in the sequence editor. I'm going to call it Preview because that's all I'm going to use it for. It won't form part of the final image process. For a quick stretch, I'm going to use the auto stretch function. There are two commands. One of them sets the shadow's clipping point in terms of number of standard deviations from the median, and the other is the overall mean. For exaggerated contrast, I'm going to bring the shadow's clipping in much closer to the median, say -0.6, and for higher brightness, I'll raise the mean to 0.2. In addition, since we haven't yet done any color calibration, I'll uncheck Link, and so each color channel will now be stretched separately, which usually gives a pretty grey looking background. Then I'll hit the lightning bolt icon, and it automatically calculates the parameters that achieve what we've asked for. There are two ways to see the result. One way is to select the preview step from the sequence editor, and this applies the stretch to the data as seen by the updated histogram. Another way is to keep the Open Image step selected and select the icon of an eye on the preview step. This then uses the preview step to automatically stretch anything that appears on the screen, and this is for screen display purposes only, not changing the underlying data. Now the first thing is that I would prefer another orientation of this image. I can easily change this by clicking on the settings or cog icon on the Open Image step, and then I can change no rotation to rotate 180 degrees. Clearly this changes the result of the Open Image step in the sequence editor, and so it loses its checkmark, and I need to recompute it by clicking on it. A next sensible step is to crop out the stacking artifacts around the perimeter by adding the Crop Image tool. I'll constrain the proportion to 2:3 and just bring in the width a bit. Next we can work on getting rid of this cast across the image from left to right, and we can do this by using the Gradient Removal tool. The tool works by sampling the background at various locations and then using the finite element method to solve the Laplace governing equation for diffusion, which I'm using to model the light pollution. The cast is then subtracted, leaving behind a flat background. We can use the Auto Sample tool to place samples automatically. I'm just going to use the default settings here, and then hit the lightning bolt icon. Green squares appear over each sample location, all on local dark spots, and so inevitably it has picked up a few on the nebula itself, and I just need to delete these ones. As you can see, when I click on a sample, it gives me a preview in the tool editor, so I can make sure I haven't picked up anything I don't want in the sample, like a star for instance, and I can of course reposition samples or add new ones as I wish. But generally, the Auto Sample tool does a pretty good job. I think I'm happy with that, and I can always fine-tune this later if necessary. And here is the result of the gradient removal. It looks nice and flat, but I clearly need to recompute the preview parameters as the shadows are heavily clipped now. I can do that just by hitting the lightning bolt again inside the preview step settings. This is now much better and definitely nice and flat with no cast. And here is the before and after. Now we can properly sort out the colors. The first step in color calibration is to neutralize the background to gray. If you look at the histogram, you can see that the peaks of each channel, which represent the most numerous pixel intensities, are not aligned, and in fact the background is dominated by green, with this channel shifted to the right. Of course, we can't see that in the on-screen preview because we used an unlinked stretch. To neutralize the background, I will add an instance of the background neutralization tool. I'll just hit the icon of an eye to preview the input, and I'm going to set the region of interest to a box 400 by 400 pixels in the top left corner, where there's not much nebula visible. And then I'll check the Show Mask box to indicate which pixels have been masked out in green. Currently, all the pixels are masked out, but if I raise the upper limit just slightly, more pixels will be included. Only a very small change is necessary, and now you can see that the stars are being excluded from the background sample, as requires. I won't change anything else here. By leaving the operating mode as rescale as needed, it will try to shift the channels to the right until they are all aligned, but if there's any clipping as a result, it will scale them instead. Here is the result, which temporarily looks awful. That's just because we're still using the old unlinked stretch as our preview. Now we are working on the color rendition, we need to recheck link to treat all colors the same, and then recompute the stretch parameters. Finally, we can confirm from the histogram that the medians of all three color channels are now aligned, and the background neutralization tool has done its job. The second step in rendering the colors is to set the white point, so that white things are a neutral gray. We can use the color calibration tool for this. It takes two reference images, a background reference and a white reference. The background reference is just for the purpose of making sure that the neutralized background we just created is not affected. We can set that in the same way as we did in the background neutralization tool, although I have retuned the upper limit a little. And the white reference is based on the idea that the average color of a large enough star field should be white. If I check the Show Mask box, you can see that it automatically masks out everything except for the stars. Stars are detected by decomposing the image into scale planes using wavelets. Stars are almost always captured very well as the combination of the second to fifth scales, so there's no need to change that. In fact, the only thing I will change here is the region of interest. And the only reason for doing this is that I happen to know that these two central bright stars are essentially white, based off their BV color index of 0.1 in the star catalogues. It just gives a slightly redder result than using the whole star field in this instance, and not only do I prefer it, but I think it's probably a more faithful color. Now, computing the output, the tool linearly scales the channels around the background pixels, so that the white reference becomes neutrally grey, while keeping the background unchanged. Here is the result, and of course I can also tweak the preview stretch again. The final step in the color calibration is chromatic noise reduction. This is a very simple but powerful step, and I find it is very important in areas where there is a lot of light pollution. Basically, in parts of the image dominated by background sky without much nebula, when we delete the background sky gradient, almost all of what is left is noise, and this leaves a very poor signal-to-noise ratio, the result of which can be a misalignment of the color channels in the background. The SCNR tool, the operation of which is widely documented in various places online, can be used to neutralize the color cast, which is usually green. The default settings are usually almost perfect. Here is the image before, and here is the result of applying SCNR. I am just going to tweak the opacity of the SCNR step a little for reasons that will soon become clear. First, however, I will turn on the Auto Recalculate option in the Tools menu, so that if I make a change to a previous step, it will automatically propagate forward to the currently selected step. Now, if I apply the preview step to stretch out the histogram, you can see that the SCNR step has pulled in the green channel from the right of the other channel peaks to the left. This is probably going to give the image too strong a magenta cast. The ideal position for the back end of the green channel is aligned with the back end of the second most dominant color channel. If I change the strength of the SCNR by setting the opacity of that step to 1/2, that seems to align the green channel roughly correctly with the back end of the blue channel. Now the color calibration steps are complete, we can consider noise reduction. So far we've only applied a rather gentle stretch. If I increase the contrast aggressively by bringing in the shadow's clipping point on the preview stretch to say -0.25, you can see that we can't get a nice clear and bright view of the nebula without the noise dominating the image. There are a couple of denoising tools we can use to help with this. The first tool I will employ is nonlocal means. This is a very effective denoising algorithm that works by replacing each pixel with the weighted mean of other similar pixels in a search window. All astrophotographers know that if you sample the same pixels over and over again for a long time and take the average, you increase the signal-to-noise ratio. Well, this tool is not averaging pixels over time, but instead averaging similar pixels over space. This tool takes a long time to run, so I will set it running with the parameters I find work best here, and then do a bit more explaining. I will reduce the patch size to 5 to reduce the effect on stars, and increase the search size to reduce blotchiness, and set it running. So the luminance and smoothing parameters specify the filter strength in units of standard deviations of the noise level for a Gaussian weighting function. Large smoothing parameters give higher weight to less closely related pixels, which removes noise more thoroughly, but also removes image details, and vice versa, of course. The patch size is the size of the square patch around each pixel used to calculate its local mean, and the search size is the size of the window around each pixel that is used to calculate the weighted mean replacement value. I find that a large search size always gives a better result, but this has a very large effect on the computation time. Non-local means is famously very effective and simple, but slow. It's definitely one that you want to leave running and come back to. So it's just finished running now, and here is the results. It's looking like the denoising has worked quite effectively. However, we don't have much contrast, which is because if we open up the preview settings, our shadow's clipping fraction is very small. I'm just going to increase the clipping fraction a little bit and reduce the midtones a tiny amount, and this will produce a very aggressive stretch with lots more contrast, which will allow us to see what the noise in the dark areas of the image is like. If I zoom in and look very closely, I can see a small-scale mottled or dappled texture in the dark areas, particularly in the top right. Another denoising tool that can be used to get rid of this is the Attrue wavelet transform. This is extremely powerful and even surgical in allowing you to remove noise and boost detail in different scales. It works by sliding a convolution mask filter of a certain size across the image and extracting how much of that filter is in the image at each location. And this gives a plane of data for that scale. And then it increases the size of the filter according to the dyadic or linear growth scheme, and repeats to get the next scale layer, and so on. It allows you to decompose the image into structures of different sizes, denoise or sharpen the detail in each layer, and then recombine them into an enhanced version of the image. I'm going to use 6 dyadic layers, but in general you can use as many or as few as you like. Dyadic just means that the scale of each subsequent layer goes up in powers of 2. And when I select a layer, I want to preview it with a gamma correction operation to increase the contrast. Here is the first layer. Areas that are darker than 50% grey are reducing the brightness, and areas that are brighter are increasing the brightness. For the first layer, I will just deactivate it entirely, as it will mainly contain noise, which means it will not be included in rebuilding the final image. And then for each subsequent step, I'm just going to increase the noise threshold, and initially reject all pixels below that noise threshold, but then just reduce the amount down to 0.8, because we don't want to eliminate noise entirely. We can then just go to each scale or level, adjusting the parameters to our taste, which I sped up here just for the sake of time. And here is the result. You can see that the mottled texture has been eliminated. We've now finished working on the linear data, and it's time to take it non-linear by stretching it out. We want to make the difference between the dark pixels greater and the difference between the bright pixels smaller, and this will allow us to see the faint nebula but not blow out the stars. So far we've been previewing the data with a non-linear stretch using the histogram transformation tool. This has been working okay, and we could probably spend some time tuning the parameters to get a result that we're pleased with. However, you can already see that this approach has led to large stars. My preferred stretching tool here is the masked stretch. The masked stretch tool applies the stretch iteratively, in small steps to achieve the target overall mean brightness. However, it uses the luminosity of the previous iteration as a mask for the next iteration. This means that the effect of each iteration is successively reduced on bright objects, and this helps to keep the star sizes small so as not to detract from the nebula, and it can help reveal bright details in the nebula that would otherwise be lost. There are various ways to use this tool, but I will set a target overall mean brightness of 0.3. Using 100 iterations is more than enough to get a smooth result, and you can change the clipping fraction to increase or decrease the contrast. I'm going to reduce the clipping fraction a little bit for just a little contrast boost, but I don't want to start revealing too much background blotchiness. And the final parameter to adjust is the upper limit, which sets which pixels will be included in the mean brightness calculation. We just want to exclude the bright stars from this. Now this has finished processing, we need to switch off the preview stretch, which would otherwise stretch the image for a second time, and then we can see the results. I quite like this result. It's soft and the stars are nicely controlled. This data is now non-linear, and we've nearly finished the processing. As one final step, I just want to bring in the shadows and highlights clipping points so that the data will span the whole range of values from 0 to 1, but without significantly clipping the data. If I set the shadows clipping point to 0.04 and the highlights clipping point to 0.96, then there are only 51 clipped highlights and only 0.14% clipped shadows, which I'm satisfied with. Now it's time to save and export the image. First I will save the Hera processing sequence file. This is just a text file that records the order and details of each step in the sequence. This means you can reopen the sequence and see exactly how you processed an image, modify things and recompute steps, or the entire process. And I will export the result of the histogram transformation step as a 16-bit TIFF for some final minor tweaks in Photoshop. And this is the image imported into Photoshop. The final operations I applied were some camera raw filter for what is essentially local contrast enhancement with the clarity tool. Then I applied some local contrast enhancement from the Astronomy Tools toolpack with some selective masking. Then I applied a curves adjustment and saturation adjustment with a mask so that it targets only the dark corners. This was to reduce the large-scale chroma noise in these areas. Then I gave a saturation boost to the nebula and a slight toning down of the purple fringes in parts of the nebula. There we go. Then some selective unsharp masking in these areas. Then a saturation boost to the stars with an inverted star mask, and then finally a star fringe correction with an inverted star mask using the optics correction tool in camera raw filter. And this is the final image.